Imagine a suspect's laptop where every browser history entry has been wiped and every file deleted. Traditional forensics stops there, but the investigation changes when that same device leaves behind a hidden operating system-level database containing an OCR-indexed photograph of everything that suspect ever viewed on their screen. Welcome to reWant Courseware, an AI-narrated series unpacking the latest lectures and thoughts from Professor Adam Scott Wandt, produced in association with the John Jay College of Criminal Justice. We are exploring a central mechanical question. How does a modern operating system construct a continuous timeline of human behavior that survives intentional data destruction? Historically, digital forensics relied on syntactic timelines, recording discrete system events like file creations, application launches, or network logs. AI-integrated systems have shifted this reality towards semantic evidence. These devices now generate searchable, OCR-indexed records of a user's actual cognitive and visual activity. This shift from syntactic to semantic evidence redefines what constitutes a deleted file. The techniques suspects once used to hide their tracks are often neutralized by a system designed to remember what they saw rather than what they saved. Navigating this environment requires rewriting the investigative playbook across three distinct domains: hardware, software, and legal. The hardware layer introduces dedicated AI processors that create new blind spots for standard acquisition tools. The software layer features operating system-level semantic databases, like Windows Recall, that continuously observe user behavior. And the legal layer presents new authentication challenges, specifically under emerging frameworks like proposed Federal Rule of Evidence 707. Isolating just one of these pillars will result in a compromised or legally inadmissible case. To successfully prosecute or defend modern cyber incidents, practitioners must master this interconnected triad of AI evidence. We begin at the hardware level. Modern edge devices have seen a massive shift in local processing power, moving AI tasks away from the cloud and onto the physical machine. This is the domain of the Neural Processing Unit, or NPU. It is a dedicated hardware accelerator designed to perform matrix multiplication, allowing the device to execute local LLM inference without taxing the GPU. In a traditional live capture, investigators target the system's main memory. Tools like WinPMEM interact with the CPU and the standard DRAM pool to image volatile state. The NPU, however, often operates with its own isolated volatile local memory pool. When an investigator uses a standard live acquisition tool today, it only sees the data in that blue DRAM pool. If an AI inference session is active, the resulting data, prompts, responses, and model states may exist solely inside the orange NPU memory. Standard tools miss this data entirely. This creates an immediate physical consequence. Executing a hard power-off on an actively inferencing Copilot Plus device will destroy these volatile artifacts instantly. First responders must now adopt a revised volatile evidence first protocol, evaluating whether AI processes are running before deciding on an acquisition method. It is a practitioner reality that authoritative, standardized extraction methods for NPU local memory do not currently exist in the field. The physical presence of an NPU means traditional dead box storage imaging is no longer the undisputed safe default for an initial forensic response. Once the physical device is secured, we move to the digital forensics laboratory to examine the OS-level artifacts left behind by that AI processing. The most significant of these is Windows Recall. It operates at the deep operating system level. Distinct from standard user-accessible application caches, Recall uses passive optical character recognition to continuously evaluate everything the user views on screen. Practitioner analysis identifies the primary target as the ukg.db SQL database. The window capture table logs UTC timestamps alongside references to a stored image catalog. Linked to those captures is the window capture text index content table, which contains the searchable OCR extracted text. This relationship allows an investigator to keyword search the user's visual history, reconstructing their cognitive activity over months. This structure acts as a powerful anti-forensics tool because it resists traditional data sanitation. While clearing a browser history might delete conventional evidence, this OS-level semantic index remains completely intact. However, the absence of recall data is not automatic proof of deliberate spoliation. It could be disabled by enterprise policy or simple retention limits. By continuously indexing visual activity rather than just logging system events, the ukg.db database forces investigators to treat the operating system itself as a highly observant eyewitness. Ultimately, the final proving ground for this evidence is the federal courtroom. Here, we face a critical gap between official manufacturer documentation and the practitioner sources used to map AI artifacts. While Microsoft provides authoritative documentation for cloud-side records, on-device local caches are primarily documented by third-party research from firms like CyberCX. This triggers a core authentication challenge under Federal Rule of Evidence 901. How do you prove the AI's OCR process didn't misread or hallucinate the data? Courts currently rely on Rule 702, requiring an expert witness to explain the process and confirm the system functioned as designed. This is why the Advisory Committee has introduced Proposed Rule of Evidence 707. Proposed Rule 707 specifically regulates machine-generated evidence that is introduced without a human expert witness. To meet these standards, investigators must perform SHA-256 hash verification at the immediate moment of collection to preserve the chain of custody for volatile AI caches. Even the most perfect technical acquisition is entirely useless if it cannot survive the strict authentication tests of the federal court system. These three pillars, hardware, software, and legal, form the interconnected reality of modern investigations. The physical capabilities of the NPU are what enables the software to build its semantic databases, and the outputs of both hardware and software must ultimately filter through strict legal standards of the courtroom. The decision to capture live memory or pull the plug on a Copilot Plus device determines whether transient intelligence survives, making initial response the most critical phase of the investigation. Because this field is moving so fast, practitioners must continuously verify artifact paths against current vendor documentation before testifying. Like, follow, and subscribe for more deep dives into emerging technology, digital investigations, and the ideas shaping our future. And remember, stay curious and want knowledge. AI forensics redefines the digital footprint. In the age of semantic computing, an investigation captures a user's perception as clearly as it captures their saved files.